This module on overlay and underlay basics will provide an overview of the two main networking types, underlay and overlay networks. It will define SD-WAN and explain its benefits, and also explain the concepts related to data encapsulation and decapsulation. At the end of this module, you'll be able to define an overlay network, define an underlay network, describe a service provider WAN solution, explain the security features of SD-WAN, and explain the concepts related to data encapsulation. Let's begin this module with an understanding of a traditional network and how it is different from a software-defined network. Traditional networks consist of physical components such as routers, switches, copper cables, fiber optic cables, computers, and servers. To forward traffic between hosts, routers use routing and switching protocols to determine the best physical path to use between the hosts. Traffic from one host to another host follows a hop-by-hop path through the network. Each routing or switching device in the path determines which next hop towards the end destination should be used to reach that destination. Routing and switching protocols are used to analyze the network topology and ensure that traffic follows the best path from end to end, and that traffic never forms a forwarding loop. In a software-defined network, there are two main networking types, overlay and underlay. An overlay network is a logical network that runs over the top of an underlying network infrastructure. The overlay network is logical because it consists of logical tunnels between remote endpoints and not physical cables. Virtual connections can be programmed and reprogrammed without modifying the underlying infrastructure. Since the logical tunnels interconnect remote locations, the tunnel interfaces appear to be directly connected to the remote devices. This creates a layer of abstraction from the physical network and hides the physical infrastructure from the device. As far as the device is concerned, it is physically and directly connected to the remote device, regardless of where that remote device may be located. An underlay network is the physical or logical network that is used to transport data from one location to another. It includes the physical routers and switches in the network. To an SD-WAN deployment, a service provider circuit is considered an underlay transport, over which the SD-WAN tunnels can be built. When a customer connects to a service provider, it's common for the service provider to provision a link or a circuit at each customer site. To the customer edge devices, or CE devices, the service provider network appears to have a single link from one edge device to another, and the edge networks appear to be directly connected. The service provider internal network infrastructure is hidden from the customer. Service provider WAN solutions have been implemented for many years to connect different company sites to resources in remote locations. A common implementation is an organization with a central office, where remote sites require access to resources within the central office. Dedicated circuits are often implemented in this type of environment, where a service provider provides a circuit or a WAN link to the customer premise, and traffic across that WAN link is forwarded through a VPN environment to remote locations. A typical service provider WAN service runs across an MPLS VPN, which is transparent to the end customer. From the customer perspective, the remote resources are a single routed hop away, where in the case of a Layer 2 VPN, remote site devices appear to be directly connected. Two main components are required to provide such an environment. The first is the underlay network, which is the framework over which the VPN tunnels are created. The second is the overlay network, which is a programmable virtual network of tunnels that runs from one edge device to another to interconnect devices over the top of the underlay network. VPN tunnels are logical network links that, to the tunnel endpoints, appear to directly connect to remote devices. They're created by adding extra header information to packets that identify the remote provider edge or PE device as the destination of the network traffic. When the remote PE receives the traffic, the outer header is decapsulated, which reveals the original header and identifies the final customer destination of the traffic. Some simple mechanisms, such as an MPLS label-to-client mapping or a tunnel-to-client mapping, are used to place the traffic in the proper routing table on the egress PE device. From a customer perspective, the service provider provisions a circuit, manages and controls this mesh of tunnels, and works to ensure a contracted level of service across the provider domain. To the customer, the service provider network is often transparent and irrelevant, as long as traffic travels from one site to another within the agreed-upon parameters. The diagram shows a simple example of a network overlay between PE devices. The PE devices are owned and managed by the service provider. The Border Gateway Protocol, or BGP, is the most common protocol implemented within the service. With an overlay or underlay topology, each tunnel endpoint is associated with a unique routing table on the PE device, which only contains routing and forwarding information related to the end customer. The traffic destination for traffic within the same customer domain is marked on the ingress PE device so that the egress PE device can identify to which customer or virtual routing and forwarding table the arriving traffic is destined. For example, traffic forwarded from Customer 1 Branch A arrives at the service provider PE device. The service provider PE device encapsulates the customer traffic with an MPLS label in the header, or the VPN site label, that is unique to Customer 1. Once the destination site is determined, the PE device performs a route lookup and identifies a tunnel that directly connects to the remote PE. The traffic is then encapsulated with the overlay tunnel header, in this case an MPLS-labeled packet with a transport label, and is forwarded across the service provider domain. Once the traffic arrives at the remote PE, the outer transit header is removed, and the inner customer header is examined, which contains information that identifies to which VRF the traffic belongs. The customer header is removed, which exposes the original header, and the PE device forwards the traffic out of the link that is associated with the Customer 1 Branch B location. In the case of multiple tenants or sites, the same outer tunnel header can be used to forward traffic between PE devices. The inner headers or site ID headers are unique so that when the PE device evaluates the site header, it can determine to which customer site the traffic should be forwarded once the site ID header is removed. Multi-tenancy often refers to just the separation of tenant data. However, multi-tenancy can also include separation of control plane information, data plane information, as well as management plane operations. A multi-tenant environment that enables multi-tenant management provides tenant access to the management platform and maintains separation of different tenant environments so that the actions of one tenant cannot impact the environment of other tenants. A service provider network links customer sites with private point-to-point links, meaning that there is no public network access through the service. There are several methods of providing access to outside networks through a service provider. One method is to provide a public internet access circuit at a centralized location, such as a corporate headquarters. This is referred to as a central breakout. With this method, all traffic from remote sites is forwarded to the central location, where security gateways and other traffic management services can be applied to the traffic as it enters and leaves the private domain. A second method of providing access to public networks is by implementing a separate internet circuit at the site itself and directing traffic that isn't internal to the company network towards the public network. This is referred to as a local breakout. With this deployment, security services should be implemented at every public access point to the network to help prevent security breaches and to enforce corporate policies. In either case, the public circuit can be provided by the same service provider that provides the site-to-site WAN connections or a separate service provider. A simple public internet connection is often many times less expensive than a dedicated WAN link. Whenever access to a public network such as the internet is provisioned, steps must be taken to reduce the risk of a security breach through that public access point. With a centralized internet access point, external traffic is often passed through a security domain that tries to reduce the risk of data loss, network breach, infiltration, virus infection, and numerous other security threats. With a distributed internet access domain, the threat domain expands to every point where public access is allowed. The same types of policies and functions must be implemented at every potential point of entrance into the network. The question then arises, if you can have a more affordable public internet connection at every site, can those internet peering points be used to forward traffic between sites? The answer, of course, is yes. However, there are some drawbacks to this design. First, security services must be put in place at all internet access points. Second, devices that are capable of providing secure tunnels between sites must be put in place. And third, but not least of all, is that it places the burden of creating an overlay of tunnels on the end customer rather than the service provider. Another key aspect of using internet links between sites is the nature of the public internet. There are no SLA capabilities over internet links, no guarantees of delay, bandwidth, and jitter, and so forth. There are valid use cases for internet transit tunnels, though. A common practice is to rely on service provider circuits and the SLAs associated with those contracts as the primary communication path between sites, and to use an internet-based circuit as a backup in case of problems with the service provider. Using a public connection for a backup in case of emergency is much more cost-effective than provisioning a dedicated private circuit just for backup purposes. But again, it requires that the customer provisions and manages the backup tunnels and all of the additional management and security functions associated with that task. When an enterprise takes on the responsibility of provisioning their own overlay network, even if it's just for backup purposes, they inherit many of the same functions that the service provider manages on the private circuit. The image on the screen shows an example of the additional devices and resources required at a single branch in order to provide an internet backup link. Although the diagram shows two different routers, one for the public circuit and one for the private circuit, the same router could be used if it is owned by the organization and not by the service provider. The customer edge or CE device is the main point of entry and exit from the branch. On the private WAN link, remote destinations are internal to the organization, and therefore a dedicated security device at the connection point may not be as critical. The public access point, however, requires additional services such as stateful firewall, IDP and IPS, antivirus, web filtering and monitoring, SLA, and traffic performance monitoring. In addition, if a guest wireless service is implemented, which is increasingly common, the ability to manage and monitor the guest wireless network is critical to the security of the entire enterprise. If a branch is compromised, the rest of the company network all the way to the headquarters is compromised as well. The additional services required at each branch can place a tremendous cost and management burden on a company's IT resources. Imagine the network in the diagram, but increase the number of branches and related devices, security policy enforcement, configuration validation and implementation, and so forth to hundreds or even thousands. Then consider the manpower required to configure, validate, monitor, and maintain such a network. When an organization deploys an SD-WAN implementation, they are extending the functions of the service provider network into their edge devices, and they are creating their own tunnels between sites. The customer tunnels can forward traffic over the service provider tunnels with tunnels within tunnels, or across public network links, such as broadband internet circuits. The goal of software-defined WAN, or SD-WAN, is to help automate control of the complexities that are involved with a WAN deployment, and use software services to perform complex and redundant tasks. Rather than manually configuring point-to-point tunnels in full mesh or hub-and-spoke designs, and all of the routing protocols, security policies, monitoring policies, SLA management, and logging functions between the sites, software is used to centralize and standardize these functions across the domain. The end goal is to create a single, secure, common encrypted network that can use the private WAN, public WAN, lease lines, or any combination of available circuits in an intelligent, efficient manner. In addition, a properly implemented SD-WAN environment should be able to transparently switch networking sessions between circuits on an as-needed basis, without interruption of services. When an organization takes on the role of WAN management, the IT requirements within the organization increase. The new role of the organization is to configure and manage another overlay over the top of the existing overlay and underlay networks and to extend a logical network into the sites themselves. This essentially extends the PE device from the service provider cloud to the corporate edge or CE device. From the perspective of the new overlay network, any circuit that connects to the site edge device is an underlay network. It doesn't matter if the new underlay consists of an internet connection, an MPLS service provider connection, a dedicated leased line, etc. An overlay can run over the top of another overlay transparently and considers the underlying overlay an underlay transport network. To provide reachability between sites, multi-protocol BGP or MPBGP is used. MPBGP allows extra information besides standard IP routing information to be transmitted in BGP updates by using extended route property information that can be associated with individual sites. The benefits of implementing a customer-managed SD-WAN solution include greater control by the customer of traffic that passes between sites, greater flexibility over which links are used for different traffic types, greater visibility of the network performance, and the ability to act upon changes in the performance of WAN links. Data encapsulation or tunneling is what makes an overlay network possible. With data encapsulation, the original data is preserved and wrapped within another header. The outer header is used to transport data between network edge devices and across a WAN link. As the data transits the WAN link, the inner data, which may include customer private address space and business-critical data, is transparent to the transit devices. Because Versa Networks SD-WAN uses encrypted tunnels for data transport, all customer control and production data is encrypted and secure, regardless of the WAN transport method used between sites. IPsec encryption is used to secure the data and control information. In addition, VXLAN encapsulation is used over the top of the IPsec encapsulation. It's important to be aware that any time data is encapsulated in a network, the payload size of a packet is reduced due to the extra header information added to each packet. The concept of data encapsulation is something that most people may already be familiar with from a different perspective. A simple example is the global mail system. When a person writes a letter to someone in a remote city, the name and address of the sender and receiver are listed on the outside of the envelope. This information identifies to whom the information is intended and who sent the information. When the letter is placed into the local mailbox, a mail carrier from the local sorting facility picks up the letter in their pre-assigned route. The letter is placed in a box and is combined with all of the other letters that are picked up on that route. The mail carrier takes the box of letters that were picked up on the route to a local sorting facility, where the end destination is examined. Based on that end information, a remote sorting facility is chosen that corresponds to the location of the destination address or region. All letters destined to the same general area and that are serviced by the same remote sorting facility are grouped together in a bigger box or shipping container. The shipping container label does not have any information regarding the actual destination addresses of the multiple letters within the container. All it has is the outer facility destination. That shipping container may pass through multiple shipping relays on the way to the remote sorting facility. The container can travel by truck, plane, ship, van, or through a combination of transportation methods depending on whether the container is labeled for overnight delivery, standard delivery, and so forth. Regardless of what transport method is used, every relay has the same destination sorting facility on the outer delivery label. Once the container reaches the destination sorting facility, another sort takes place where the boxes of letters are placed in a truck that services a group of end businesses or homes. The driver of the route gets in their truck or van and begins the process of following the route, and only then does the final address get examined to determine which end house will receive each letter or package. Once the letter or package is delivered to the proper house, the end recipient can open the package and view the contents. At no point in the entire process are the contents examined by the carrier. Data encapsulation or tunneling is similar in many ways. An end host creates a data packet with a source and destination header that is used to identify the source and destination host machines based on IP address and protocol delivery information such as TCP or UDP delivery formats. The end host sends the data packet to a switch or a router, which examines the outer address information to determine the final destination. Using routing and switching tables, the packet is forwarded towards a gateway, or a device that has reachability information related to non-local destinations. This would be the CPE device. In an SD-WAN environment, this is the SD-WAN edge that connects to the various carrier environments, whether they be LTE, broadband, or dedicated MPLS circuits. Regardless of which of the circuits is used to deliver the data packet to the remote site, the remote site is the same, similar to a remote sorting facility. The CPE device wraps the original data packet up inside another header or outer delivery address that is specific to the remote site's LTE, broadband, or dedicated MPLS-facing IP address. The transport network forwards the encapsulated packet towards the CPE device using standard routing processes. Once the encapsulated packet arrives at the remote CPE device, the packet is unwrapped or decapsulated, and the remote CPE examines the original destination address, which is reachable through a local internal link. The original packet is then forwarded on the private internal link towards the end host. During this process, none of the transport devices examine or process the original data packet header and address information. All of their processing and forwarding decisions are made based on the outer transport information. This process of wrapping the packet up in an outer header is called tunneling. The tunneling process can either wrap the original packet up in the same format in which it was received, or the process can encrypt the original data before it is placed in the wrapped-up packet to ensure that anyone that intercepts the packet during transit can't open the packet and read the internal contents. Some common methods of encapsulating traffic include GRE tunneling, which places the original unmodified packet within the payload of the encapsulated traffic, or IPsec, which encrypts the original data packet before placing it within the payload of the encapsulated packet. The image shows the encapsulation format for both encrypted and unencrypted data in the Versa Networks SD-WAN solution. There are both secure and cleartext tunnels created between devices. The secure tunnels are used for control plane information and customer data. The cleartext tunnels are used for IKE negotiation and secure tunnel maintenance. Because IPsec requires keys that change over time, a cleartext tunnel session must be used to exchange the key negotiation parameters. Otherwise, once the keys refresh, the new keys would not be able to be sent to the remote peer, as the tunnel would have expired. You can't send keys across a secure tunnel to refresh the tunnel itself. This process follows the industry standard IKE exchange process to build and maintain IPsec tunnels. When overhead is added to transit packets, the MTU of the links throughout the domain must be considered. Jumbo frames are supported, but a customer has little to no control over whether a service provider or broadband connection will support those frame sizes from end to end, and potential MTU issues across the WAN must be taken into account during design and planning, and for troubleshooting should any network reachability issues be observed. You have reached the end of this module. In this module, you learned an overlay network is a logical network that runs over the top of an underlying network infrastructure. An underlay network is the physical or logical network that is used to transport data from one location to another. A common WAN implementation is an organization with a central office, where remote sites require access to resources within the central office. Versa Networks SD-WAN uses encrypted tunnels for data transport, and all customer control and production data is encrypted and secure, regardless of the WAN transport method used between sites. Data encapsulation is similar to the pickup and delivery process followed by the global mail system. Secure tunnels are used for control plane information and customer data, and clear text tunnels are used for IKE negotiation and secure tunnel maintenance.